Welcome everybody to the Washington Statistical Society seminar today. My name is Katherine Irimata and I will be the chair for today's seminar. I'm the current WSS methodology program chair and we'll be organizing a number of seminars for this year. So we're excited to have you at our first one. Today we're having a talk on doubly robust estimation for non-ignorable non-response by Dr. Michael Bailey. This is particularly important and relevant nowadays as we increasingly have access to non-random survey data, but we'd like to make population inferences. So in a few minutes, I'm going to turn it over to our speaker for the presentation, and then afterwards, there's going to be time for questions. If you have any questions during the presentation, you can go ahead and put it in the chat, and I will let Mike know, and he'll stop to address it as there's time. At the end, we'll also have time to answer questions from the audience. So everyone's muted right now, but you can raise your hand and we'll unmute anyone to ask questions. So I'm pleased to introduce our speaker, Dr. Michael Bailey. He is a Colonel William J. Walsh Professor of American Government in the Department of Government and the McCourt School of Public Policy at Georgetown University. His research and teaching is on public opinion polling, American politics, and the Supreme Court. He's the author of Polling at the Crossroads, Rethinking Modern Survey Research, which is due out this spring, 2024, from Cambridge University Press. He's the author of 2 statistics textbooks, Real Stats Using Econometrics for Political Science, and Public Policy and Real Econometrics Using Econometrics for Political Science and Public Policy. And he's also co-author of The Constrained Court, Law, Politics, and the Decisions Justices Make from Princeton University Press. And he's interested in Japan and speaks Japanese as well, which is really cool. So Michael, I'll turn it over to you now.
Yeah, well, thank you, Katherine. Thank you, Shin, and thank you everyone for joining and participating. So yeah, so the big picture theme of what I'm trying to do with this and some other work is trying to really push forward and maybe push against the dominant paradigm that we have in survey research, which is very missing at random based type methods, weighting, and kind of, building off the random sampling world. And it's just becoming, in my view, less and less tenable to use some of those methods as, in the probability based polling world, the non-response rate is, through the roof. And then of course, in non-probability polls. And so that's the big picture, is just try to just keep pushing forward and try to come up with see what we can do to come up with alternatives to the missing at random based models. The specific things I'm doing in this particular paper, there's kind of 2 elements. And so one is, not surprisingly, talk about double robust estimators. I'm sure a fair number of you have seen those in action, so I'll kind of play that out a little bit. But then the second theme is my claim and experience is that once we move to a missing not at random type model, that we're really going to need, or certainly at least benefit from, having randomized response instruments. So I'll try to flesh out what I mean by that and talk through that. And actually, in both of those angles, this is work, really using what other people have done, and I'm just trying to bring it together, apply it to politics, and push folks forward in that direction. You'll see, not surprisingly, the randomized response instrument-based methods, they're certainly not perfect, and they of course rely on assumptions. But I think that they're going to make less assumptions, or a minimum different assumptions, than we've been accustomed to making when we do conventional weighting. I'm also going to show some examples where it's relatively easy to implement these things, and then show examples where I think there's some pretty intriguing substantive results about American politics that you would not see using conventional MAR, missing at random based weighting, but that you do see here. Okay. So that's the kind of big picture. Now, the way I'll do this is I'll start just talking about doubly robust estimators in the kind of conventional missing at random world. And then I'll move to doubly robust estimation in, and this is more of my interest, in the, the non-ignorable non-response, also known as the missing not at random world. So I'll talk about the randomized response instruments. I'll talk a little bit about estimating equations. So we kind of have to use a slightly different technology, as it were, in that environment. And then I'll present some specification both for a non-ignorable non-response weighting approach and a non-ignorable non-response imputation approach. And then I'll do a case study using a survey data that I did implementing some of these ideas back in 2019 from a survey where I used Ipsos data, a political survey. Okay, just to be super clear, to make sure we're all, like, I think everyone knows these terms, but just to kind of clarify nomenclature. So I'll talk about ignorable non-response, and that means that outcome is conditionally independent of response. It's also known as MNAR, and other things. People may refer to that as well, but that's the nomenclature I'll use. And then non-ignorable non-response is where the outcome of interest is dependent on response propensity. And so this is, I don't know how MNAR, but I'll probably mostly say non-ignorable non-response. And there's two sources or two categories of where we could see non-ignorable non-response. A common one certainly in the political realm is to think about there's some omitted variable, something we haven't measured that affects Y and also affects Y, which is the outcome of interest, and R, which is whether you respond. So again and again, in the aftermath of the 2016 and 2020 elections, where surveys, didn't always do so great, people would say there's something like social trust. Social trust may affect whether you respond. We don't really have measures of it. We certainly don't have weightable measures of that. So it may affect whether you respond. And it could be that the people who are low in social trust could, for example, be more supportive of Donald Trump. A related, and these actually aren't like opposite views, but just from modeling perspectives, or maybe theoretically, we could just think of a source of non-ignorable non-response as where Y, the outcome we're trying to measure, directly influences response. So in that example, it might just be like, even when you've controlled for all kinds of covariates about education and so forth, it could just be people who like Trump are less likely to respond, right? And it may or may not be, but there certainly could model that as being the case. And then other environments, like in public health, whether someone responds to be tested for COVID or whatever. So whether R could depend on Y. You're trying to measure whether someone has COVID, and it well could be whether someone has COVID could make them more likely to get tested, even in a randomized, even when folks are trying to do randomized testing and so forth. And then marketing. In marketing, the case might be, it turns out that actually people are more willing to respond when they like a product. And so their Y, the thing you're trying to get at, whether they like a product or not, could actually directly affect R. And of course, it could go the other way. Whether you hate a product may make you more likely to respond. Either way, those would be places where Y, the view we're trying to, the characteristic we're trying to measure could affect R. Okay, so there's just some nomenclature and just get us all lined up on nomenclature. Now let me just talk about doubly robust estimation in a missing at random context. So this is not really my interest, but although it's an interesting set of results and methods and so forth, but just to kind of lay out what a doubly robust estimator might look like. And I'm really just here just giving you back what Chen, Li, and Wu have done in their paper. So there's two types of estimators in this view. One would be weighting, and then we've seen weighting. Pi hat is the probability of response. And then your measure, we'll just do simple, measure of the mean value in a population would be the weighted value, where R is whether you respond or not, Y is your opinion, the thing we're trying to figure out, and pi hat is propensity to respond. Related but different, we could think of an imputation type approach, and there, let's imagine Y hat 0, or Y hat 0 is my notation to say the probability Y equals 1 given R equals 0. So this is the people who didn't respond. What are their opinions? And if we have missing at random, then as you can see in that second line there, the probability Y equals 1 for the R equals 0 folks is conditional on the covariates, the same as the probability Y equals 1 for the R equals 1 folks. You can then patch together an estimator there at the bottom where we put together the actual responses, the RI, YI, and then we also, for the people who didn't respond, that's the 1 minus R, there should be an I there, I guess, is the imputed value. Okay, so there's a weighting and imputation, often going to point in the same direction, but they are conceptually distinct. In a doubly robust estimator, is you do this thing, which looks a little obscure perhaps at first, but I'll just kind of walk through it. Is there's a an estimator where you basically are taking some weighting element and an imputation element. And so now I've just rewritten that in two ways. And in fact, well, anyway, in fact, I think there's a typo in that Phil pointed out. I know Phil's on the call. He pointed out earlier and I didn't correct it there, but here's the correct, but you'll get the general idea. Is in the top line, suppose that your imputation model is correct, right? So you have either your imputation model could be correct, your weighting model could be correct, or both could be correct, or neither could be correct, right? So there's 4 different possibilities. Let's suppose that your imputation model is correct. As you look at that top line equation, you'll see that yi minus, in a MNAR context, yi minus the yi hat 0, that's going to go to 0, and you're just left over with the imputation. But I just said the imputation was correct. So in the top line, if your imputation model is correct, you should be getting the right results. In the bottom version, which is just a restatement, just algebraic restatement, now let's suppose that your weighting model is correct. That would mean on average, when people respond, the r minus pi I and kind of the right-hand side of that, that thing on average is going to go to 0, because on average, you're getting it right, whether people have responded. And then what's left over, so that right-hand side kind of goes to 0, and then what's left over is a conventional weighting model. But that was under the supposition that the weighting model was correct. So there again, you are correct. So if just one or the other is correct, weirdly, and I think people were quite excited as they kind of developed this, and this was not me, of course, developing this. In fact, I'm sorry, I don't have the sites for that. Obviously, I can get those for you. The doubly robust can get you the correct answers in either way. So I think the best way to explicate that point is to do a simulation. This is just kind of a one-off, and then the papers that I'm citing have done kind of a more thorough, but just to give it a thorough working through different simulations with broader set of possibilities. But let me just give you just to give you a flavor of how this might look. Suppose that the true response model depends on x1 and x2. And also suppose that the true outcome model depends on x1 and x2 as well, right? And so that's kind of a nice missing at random kind of world that we might picture seeing. But suppose you misspecify the weighting model and you just don't include any covariates. And in that case, it's kind of a silly model, just everyone's going to have the same probability of responding. Or suppose, I'm going to do the different versions here in a figure in a second. Suppose that you, in your outcome model, when you're trying to impute, you don't have x1 and x2 in there. So you're just assuming, you're just imputing the average value to all the missing folks. So those misspecified models are pretty bad, actually, right? They're just kind of just imputing averages for folks. So let me just walk through the kind of 2 by 2. And again, this will just give you a flavor of a doubly robust if you haven't seen these before. So here is, let's suppose that we have, our models are true, meaning we actually use the correct models. In a moment, I'll use the incorrect models, but just to get us going, we're going to use the correct models. I've set up in the simulation that there actually is some non-response bias, right? The x1 and x2s, the people who respond, are not representative. This is just a classic, like, there's too many older people, there are too many college-educated people, and so forth. So whether you use weights, imputation, or doubly robust, you're going to get it right. And so that's consistent with missing at random type approach. But now in this second figure, the bottom figure there, let's suppose that your weighting model is actually correct, but your imputation model is bad. So remember, I showed like a pretty bad imputation model. I just imputed the average value of y to all the non-respondents. I just said their value of y equals what the respondents' average was. So it's not, I'm not even trying really, right? But the remarkable thing, again, this isn't a simulation, is you can see that the doubly robust model kind of lands on the weighting and not on the incorrect imputation. And then the flip side is, you now suppose that you use that bad weighting model, but a good imputation model, right? So in the weighting model, you don't do any covariates. In your imputation model, you do use the correct covariates. The doubly robust, again, kind of saves you from that. And then, we do need to, of course, note that if you're just bad and bad, like if everything's bad, you can you're not going to solve the problem, right? So it's the doubly robust is not perfect, and you got to get at least one of them right. But typically, people are excited by the possibility that now we have 2 bites at the apple, as it were. And there's a literature here, like trying to figure out when, and maybe you could be a little bit wrong, and maybe you still do better with doubly robust and so forth. But I think there's a fair thing for us to say is, if both your models are wrong, you're not going to get it right, or certainly the potential for getting it wrong is there. Okay, so that's the spirit of a doubly robust estimator in a missing at random world, just to get the idea of what doubly robust is. My interest with this research agenda is in the missing not at random world, in a non-ignorable non-response world. And as you can imagine, once we go into that world, we got a lot of things to work on, right? It's going to be harder. So let me flesh out that a little bit. So just as I said before, when we have non-ignorable non-response, the probability of selection, and here I really probably should say response, the probability of response depends on the outcome. So R depends on Y. And so here I have a simple example where the probability that someone responds is conditional on X and Y. And so the gamma Y and Y, that's the key term there. That's missing at random world, we assume gamma Y equals 0, but here we're going to allow that to be non-zero. If you just wanted to go and do the typical weighting, you're in trouble right away, right? Because you can't run your response equation because you haven't observed Y. So you only observe R equals 1 people. When you have Y, and you want to put a parameter on that, of course you only have R equal 1. You only have the people who responded. So the conventional way to do weighting is, pretty clearly not going to work here. So sorry. So we're gonna have to do something separate, something new and different. And before I get to that, try to work through that, I just want to make a point that's Zhao Meng and others have made, is that when the stakes are kind of high, let me just say that. So if it's a case that gamma Y is not 0 and we have non-ignorable non-response, things could go wrong quickly. And let me just explain that with what I call the Meng equation from Zhao. This is Y bar lowercase n is the sample mean. Y bar capital N is the population mean. So this is just how far off the sample is from the population. And there's a number of, a lot of folks have done different versions of this and so forth, but I happen to like what Meng has done here because it's pretty clean. And this is just this is an identity. There's no asymptotics or no inference or something. This is just I'd be happy to point you to, or even I might even have the notes here to show you the derivation. It's not a complicated derivation. And the key thing here is that the row RY, the left term after the equal sign, that's the measure of how much non-ignorable non-response is. That's the measure of the correlation of R and Y. And loosely speaking, if gamma Y in my previous equation is non-zero, then rho RY will be non-zero as well. It's actually a little complicated. There's some subtlety there, but commonsensically, that's the thing. And then the thing that Zhao really emphasizes, which I think is interesting here, is you notice then there's what I have highlighted here is a data quantity component. And there's a lot to talk about and a lot to unpack. And actually some people kind of argue about this. And but there's a capital N in there. Capital N in my notation is population size, lowercase n is sample size. And so suddenly you've got the population size interacting with the non-ignorable non-response measure, the rho RY. And so here, to the extent that this is going to be how we want to characterize things, is suddenly we see that just having non-ignorable non-response is going to interact with this big number n, and really things can go haywire pretty quickly. Anyway, I'm happy to talk more about this. I won't really lean on this equation per se. I'm really just using this to say, in our world, when we are post-random sampling, or certainly, at best we have random contact, and then there's optional opt-in for the people who are randomly contacted, or we have non-probability samples, it seems plausible that rho, R, and Y in some contexts could be non-zero. And then this illustrates that, at least in this formulation, suddenly that thing's going to lead us astray pretty quickly. And, we have this intuition, if you have a non-random sample of some sort, things can go bad quickly, and you could probably make that point in other ways as well. But I'll use this to make that point. Okay, so in a non-ignorable, non-response world, things can go bad quickly. Let's just take it. That's the point. So it's worth trying to solve this. Obviously not the first person to say this, but there's a few different ways you can do this. You can do parametric assumptions, the Heckman selection model. There's a lot of copula models that really allow for many more different kinds of relationships between the error in the two equations and so forth. Pretty cool, but if you're only trying to identify these models based on these parametric assumptions, in the book I've have been working on, and just in others, and again, not unique to me, that's very fragile, and you really your mean squared error in those things tends to be very, very high. And so I'm not super enthusiastic about only relying on parametric assumptions to try to identify those kind of models. But what I'm more excited about, and they're not perfect, of course, but is if you use randomized response instruments. And then I'll talk about creating a weighting model or an imputation model. So both sides of the doubly robust. In that context, now suddenly you have data, you have information that now can be fed into the non-response model that's going to pin it down. In the book, I show simulations how once you have a randomized response instrument, which I'll identify in which I'll define in a second, these models behave better, and they behave in ways that you want them to. So that's going to be my focus. So, and then here, of course, I'm going to do the doubly robust version. And, if that's our approach, we just need to get one of those right. Again, maybe we'll get them both wrong and we're kind of out of luck, but it seems like a nice thing to at least get 2 bites of the apple. So, what do I mean by, or what's the role of a randomized response instrument? So I really like this paper by Sun et al. They go through and they have a fairly elaborate argument and proof of that you're going to need a response instrument to identify a fairly broad class of the non-ignorable non-response models. And a response instrument is pretty simple. It's not the exact same as the instrument in the other contexts we have, but it's going to be fairly familiar sounding for instruments in that we use in other contexts. So in this case, a response instrument is something that affects response, conditional on covariance, but does not affect the object of interest, y. So a response instrument affects R response, but a response instrument does not, in the full population, affect y, right? And so theoretically, those response instruments could be observational or randomized, but for all, you can probably kind of common sense your way to it. Like an observational, you have to make assumptions that are maybe a little harder to defend, but I'll show you if we control the response instrument, if we turn that into a RCT, more of a RCT flavored thing, then we have a little stronger argument to make that the thing that we're calling our response instrument satisfies those conditions. It'll be very easy, of course, to confirm whether or not the response instrument affects response, and I'll show that. And then, in an observational world, it's always harder if you had an observational instrument, that's harder to know whether in the full population that thing is independent of y or not. But in a randomized context, at least you can make that case. Okay. Actually, just to put a little flesh on the bones here, let me just talk about Cohn, Nate Cohn from the New York Times. They did something. I'm going to do something different, but just to give you an example in case it's not clear what exactly I mean. So the New York Times in the state of Wisconsin in the lead up to the 2022 midterms election, they basically, I'm simplifying a bit, but more or less they had a survey instrument that they're going to put out in the field on a given day. Half the people, they just did the normal way they try to get people to respond. And they got about 1% response, 1 or 2%, which is normal for what New York Times probability-based polling gets. At the same time, with the same questions as much as possible, they also recruited people where they offered them $30 each to respond. So now essentially the response instrument is whether you've been randomized into you get a lot of money to respond, or you just get the good old call or email or whatever I don't know exactly how they were recruiting people. But there's an example of a randomized response instrument. And then it's very easy for them to verify that the first condition was satisfied, as the people who got money were, I think, as it happened, were 30% response rate, which was, 10, 15, 20 times as high as the response rate, or 10 or 15 times as high as the response rate in the control treatment. I'll do something different, but that's the spirit of I would love to get that data, by the way, and do everything I do here. I do not have that data. Okay, so we're going to have a randomized response instrument, and let me talk about what that means. And I'm going to talk in more detail about a weighting version of that. In a weighting version, like you see in the top line, I just am showing you that's just my notation for a weighting model, and you can write it different ways, but it's fairly familiar. R is whether someone responds. Y is the thing we're trying to measure. Pi hat is a propensity to respond. In a MNAR world, you could do that. That's the same equation we saw earlier. The catch, or the difference, and it's a big difference, is you'll notice now I've written out, I'm going to assume a logit, and you can do different things. I'm going to assume a logit for the response model. And then I put gamma y in there. So that is that's a big difference. We could not do that. We can't do that with standard techniques. But what Sun et al. Do, and perhaps others, I'm not sure if they're the first ones to do it, but they're early adopters certainly, is they use estimating equations. And an estimating equation is the following, and I know having too many equations and something like this gets a bit much, but let me just talk through the intuition. So you're going to have equations that each equation is going to impose. You're going to basically generate parameters, and those parameters then are going to satisfy a collection of conditions. And let me focus on H2 there. H2 is just saying, for example, that the weighted sum of Z, so Z is my response instrument, it's 1 or 0. The weighted sum of that equals the actual sum, right? So, because by the way, if the response instrument works, you're going to get too many Z's. You're going to, in the observed sample, so you're going to have to kind of downweight the people. You're pulling in all these people with Z equals 1, right? Because it's pulling more of them in, but you have to kind of undo that, because in the whole population, let's say Z really should be 50% of the population. But in the observed sample, maybe you're getting 60 or 70% of people with Z equals 1, because Z has brought people more in. So pi I, in that case, the fitted probability is going to have to be lower for the people with Z equals 1 in order to maintain that in the weighted population should reflect the true population. Similarly, H3, the third equation there, does a similar thing, saying the weighted sum of the any given xi covariate, say it's college educated number of people that we know from census data or whatever in standard weighting type logic. We know what proportion should be college educated, and we're going to have to weight them, and that would be among other things, the gamma x in that equation will downweight, say, college educated people if they have a higher propensity to respond. And then the thing where it does the action is the H4, the fourth equation there. That's an estimating equation. So what we're doing there is we're imposing the condition that Z and Y are orthogonal, right? And so that we're imposing the independence in that. And so that's the weighted average in the weighted population, right? That Z and Y are orthogonal. And that takes a bit, and I have an appendix in the paper and so forth, working through the intuition. This was new for me, and kind of work through the intuition of that. But one thing we can see immediately is, like, normally, it seems like it's a problem to be having a gamma Y term in the response equation. But notice in that fourth estimating equation, R is there. So if R equals 0, it doesn't really matter that we don't observe Y for the R equals 0 people. But what we do is for the R equals 1 people, that their weighted values, the Y's and the Z's have to be independent. And that's that second condition that was earlier in the response instrument. And the foundation of the response instrument was to say that in the full population, Z and Y are independent. And if you fail that condition, then imposing this condition, if the reality is you're using a Z that is not independent of Y, then that fourth condition is not appropriate to impose. But if you've created a response instrument for which that's true, this is an appropriate condition to impose. And the upshot is, and again, I know, like in a talk, it's a little hard to see all the pieces, but the upshot is, and we'll implement this momentarily, the upshot is that you are able to estimate a gamma Y parameter. And the gamma Y parameter then will tell you, like, to what extent is it the case that if Y is high, you're more likely to respond. And super goofy, honestly. It's super weird to then suddenly have you're getting in your data and you're going to upweight the people who say, who are, support Trump or whatever, if that's the thing you're trying to estimate. But we'll see examples of that, how it works. And I'm happy to try to, I'd love to be able to really make that as intuitive as possible. I'm not sure I'm there, but certainly this is schematically, this is what is done, and it will produce. And by the way, it will produce things that are pretty sensible that we'll see in a little bit. So, okay, so we're going to use estimated equations. And the key thing is that estimating equations allow us to estimate an equation that is consistent with at least one articulation of a missing not at random model. Okay, so there's assumptions. I probably don't even have all the assumptions here, but we're going to, like the never responders, like if those of you who've done like Mansky bounds and so forth, like if the never responders never, ever respond and so forth, and they could totally be different, you're going to be in trouble. You're going to be in a lot of trouble in a missing at random world as well. So we're going to have like each type of person has a non-zero probability of responding. Might not be true. It's not also a problem in MNAR models. This is the instrument that just the conditions we talked about. There is going to be a monotonicity, and it is going to be local. And so you could imagine, and maybe in the discussion, we'll talk about, like ideally you'd have many different types of cuts at this, and you'd have different types of response instruments, and that would maybe address or ease concerns about the localness of it. But we're going to, for a Z that pulls in another slice of people for any given, population, you will locally identify that gamma Y parameter. And then this is that the Z, the instrument, it cannot interact with Y. And so this is like the fourth condition there. That's a binding assumption, and that's may or may not be true. But let me just flesh that out a little bit. So here, you see imagine that the response equation, the probability someone responds is a function of Z, the response instrument, X. I'm treating that as like standard demographic covariance we'd use in weighting, and Y, the thing we're trying to measure. And you'll see there's a bunch of interactions, and I think it's all the different interactions for this simple model. You'll see that there's Z has some effect, but we're also easily able to, in this model, allow Z to have different effects for different demographic groups. So that's the ZX interaction. I don't know if you can see my circling, but I'm trying to highlight that. You also can allow Y to have different effects on different groups. So the extent to which there is non-ignorable non-response could be larger for college-educated people or larger for, you name it, right? That's totally fine. The thing that we do not allow in these models is this last term. So that's the thing that we have to wipe away. And, so it's an assumption and may or may not be true. And folks can probably come up with scenarios where that's not true. But let me just make the point, and this would be one of my general points, is that missing at random models make a bunch of assumptions. They assume Y doesn't matter. They assume Y doesn't interact with X. They assume Z doesn't interact with X. And whereas, at least in this formulation, this model will make only the assumption that Z and Y don't interact. Okay. That's the one I'm going to kind of lean on a little more and explain more. And to me, I find that relatively more accessible. I'm now going to talk about the imputation model. The imputation model is, honestly, I just am more really relying on the work of others on this, but let me just kind of highlight it, and then I will implement it, and we'll see the implementation. And by the way, we'll see, at least in my results, the weighting and the imputation end up pretty similar, and then hence the doubly robust end up pretty similar. So we're not getting a big, a divergence between weighting and imputation that, such as I was in the examples I was showing earlier, the simulation examples. But let me just make the point to lay out the groundwork of how an imputation model would work. So imagine now we're going to allow Y, the response, and R to have some joint distribution. And then this is their work. That's a pretty, there's a lot going on here, but you see the first term, there's an eta in there, and the eta is what they have defined as the non-ignorable non-response function. it's a function. In the logit model, it just, if we assume logit distributions for these things, this thing just reduces to a single parameter. It could be more elaborate things going on. But the key thing is, so they've decomposed the joint distribution, and there's a lot of work that went behind this, right? So this is not just this should not be obvious. It is not obvious. But the key thing just to note here is that when they have, it's a function of something about the non-ignorable non-responseness going on, and it's also a function of f of y for r equals 1. But notice now z is in that equation. So even though we've assumed z has no direct effect on y in the full population, in the subpopulation, z can have, there can be a conditional relationship, right? And it's just the non-response has made it such that the people that z now could be explaining their behavior. So I'm just skipping down here just to give you the spirit of it. So from that, they do a little bit of work for, marginal distributions. And now they're going to have the distribution of y conditional on r equals 0. That's the bottom equation I have here. And there's kind of a lot going on here. But again, it's going to be, well, what it reduces to, it's some function of the non-ignorable non-response relationship, which in the examples I've been showing you really is going to depend on gamma y. It's going to depend on the extent to which y affects r. And then it's a function of y, but for the r equals 1 people, that depends on z. And so the thing is now that for the distribution of y for the r equals 0 people depends on the distribution of y for the r equals 1 people. And since we observe the distribution of y for the r equals 1 people, maybe we can make this work. So let me just talk to you about how this would work. So you would go through the steps in this imputation. Is we can estimate the distribution of y for the r equals 1 people. And then again, the kind of weird thing, but we're allowing z, again, in the whole population, z has no effect on y. But in the r equals 1 people, via the selection process, and this is just standard selection, this kind of thing happens in selection a lot, right? Z can be predictive of y. And so you write down, they do usually a saturated model of this. I'm just giving you a, small version of this. But so now you've estimated y as a function of x, z, and perhaps some interactions. You go back and use that equation that I just had on the previous page. That would then be the distribution of y for the r equals 0 folks. And now you're able to, it's a little hard to see in here, but you're able to impute, right? If you know f of y given r equals 0, which is a function of f of y given r equals 1, you're able to get a number out of this, right? And so in other words, they're able to impute this. And then now this is then, we are then going to say in the full population, z. So now the thing in brackets here with the r and the 1 minus r, I'll fix that. That is the full population. In the full population, y should be independent of z. So we're imposing that second condition for instrumental variable here for a response instrument. If you impose that, let that thing work through the system, and you will get estimates of, well, you'll get an average estimate of this, and you're really in the implementation from Sun et al. You'll get an estimate of gamma y, and gamma y is essentially allowing you to calculate the relationship between r and y. Okay, so all right, so doubly robust. I'm actually going to go, it's going to be the same logic. There's some nuance here, but just in the interest of time, I'm just going to show you. And I think just visually, you'll get the idea, because I do want to get to the results, the empirical results. I'm going to go through, I set up a model. I set up a model where there in fact is non-ignorable non-response. I'm going to estimate it under 4 conditions. First is where we have both our weighting model and our imputation model are correct. Right, we see if we just do the traditional weights, they're going to be wrong. The true value is 0.5. The estimates are wrong. It's not surprising at all. I set it up that it's non-ignorable non-response. Of course, a missing at random model is not going to get that. If we have them both right, we get it right. Here, if we have the weighting model, split right with the imputation model wrong, doubly robust still gets us the right thing. Or if we have the wrong weights, but the correct imputation, we get back to essentially the right thing. And then if they're both wrong, we're wrong. So this is just, it's one example, but again, it carries over that same flavor we showed earlier. Okay, so what I really want to do is I want to get to the empirical results. So this is an Ipsos survey in 2019. Ipsos, this is their, gosh, I'm forgetting the name of their panel, but this is the one where they have a random sample, or they've recruited a random sample, or arguably a random sample, and we could debate how much they've achieved that, but that's the goal here. Then we're implementing a survey. They asked 3,500 people to respond. 2,200 people responded. 1,300 people just didn't respond to the emails. We're going to assign everyone really to control and treatment. And this picture is a little awkward, I appreciate, but could have put the control and treatment earlier, but just to make the picture at the bottom work, hopefully you'll just get the idea. Or just to rephrase it, of the 3,500 people, I've assigned them to a control and treatment, right? And I just happen to be dividing it this way. In the control, I'm going to be asking them questions right away. I'm just, hey, what do you think about, let's say, what do you think about Donald Trump? In the treatment group, I'm going to allow them to leave, essentially. So I'm going to lower, the control group is going to have a higher response rate because I just ask them right away, and very few people at this point don't answer. In the treatment group, I'm going to do the following is I asked them, do you want to talk, and it's randomized, but do you want to talk about politics, movies, sports, or health? And about 40% in this survey. I actually have another one in the field where it was 20%. I'd rather it's 40%, honestly. But so a lot of people leave, but it produces the following layout, which is the people we just ask questions, they respond. There's 1,100 of them. The people in the treatment group, about 40% of them stuck around and said, yeah, I'm going to talk about politics. And about 60% of them left. And what we're going to treat for these purposes, by the way, there's other analyses I don't have time to talk about now. We can slice this different ways and we're going to end up with similar conclusions. But I end up with a data set of 1,500 people. In that 1,500 people, the control group is, it turns out, the high response group. So they're responding at, you really want to take 1,100 divided by 1,100 plus 678. So about 2/3 of the control group in the original are responding. And the treatment group is 300 divided by 713 plus 677. You can do the math on that faster than I can. But so there's the treatment group are the people who are the low response propensity, right, by design, right? Because I said, hey, if you want to leave, you can leave. And so we're going to be treating the people who never showed up in the first place, and also the people who leave, we're going to treat them as non-respondents. Again, this is not the only way to do this. This just turns out to be a really easy way to do this. It's quite cheap. What Nate Cohn did at the New York Times is at some level a better way, but he was paying $30 a pop for the respondents, and so that was pretty expensive. But broadly doing what he did, what I did, or doing other things, I'm more than happy for people to experiment with things. Let me just show you where this leads to. And so I'm going to just do a few empirical results, but the point will be, this is for that one survey. I've done this I've done it 4 times. Josh Clinton did it once at Vanderbilt. I always get the same results on turnout. And the thing about turnout is we have a pretty strong belief when we ask people if they're going to vote, we tend to get higher, more people saying they're going to vote than actually vote. And obviously there's lots of people doing verification in all kinds of different ways. I did not do verification here. This is prospectively whether you would vote in the upcoming elections. This is 2019. We're asking about 2020. A lot of give there, but nonetheless, just in general, I think it's fair to say we suspect that the turnout vote is going to overstate things because the type of people who respond to polls are the type of people who also like to respond. Right? That's not at all original to me, and that's a very, very common suspicion that people in political polling have. So I asked the survey, it's on 5-point scale from absolutely to that they will vote to down to they won't vote at all. And I'm just only going to keep the absolutely for this purposes, but the results are pretty similar if we slice it different ways. So a lot of people say they're absolutely likely to vote. I'm going to estimate this model, and I'm going to allow that gamma y in that weighting model. Again, that's weird, right? But that's my broader claim also, is once we get into non-ignorable non-response, that's what we meant by non-ignorable non-response. So let's see if we can, in fact, estimate that using estimating equations. We can estimate it. And now let's see if we believe it. Using conventional covariates, can talk about the imputation. So in the, sorry, I'm having a little bit of problem here. The gamma y parameter, obviously in the observed and weighting, conventional weighting, that's 0 by assumption. And then we have a positive gamma y parameter in all the, whether we do weights, imputation, or doubly robust. Pretty big standard errors. What does that mean? Sorry, I'm having trouble with my mouse. For the estimated mean turnout. So this is just the estimate. More carefully, that's a little bit imprecise. This is just what's the in that survey, what's the estimated proportion of people who say they are certain to vote? In the observed sample, it's about 77%. When we weight it, it goes down to maybe 74%. But when we do this method, which is now down weighting, counterintuitively, I know, but down weighting the people who said they're going to vote, but there's there was a model. And by the way, in other models, we're going to get zeros on gamma y's, right? So it's not that we always see non-ignorable non-response, but here we do. And we get quite, now we're down to, 55% or so who say they are certain to vote. I don't have an on the ground benchmark here, but I would say, and perhaps some of you know better than me, but in the midterm election, are we at 60% turnout? I don't think we are at 77% turnout or 74% turnout. And that's just of the certain to vote, to say nothing, because the next category down was very likely. And, it seems consistent with the idea that there could have been non-ignorable non-response in turnout. So I'm going to do two more things, and then I'm eager to hear your questions. Another thing that people are, of course, interested in politics is Trump approval. So here, did all that stuff that we talked about, we estimate gamma y. For the entire population, that's just a 0. So there was no sign overall in 2019, using that Ipsos survey, using the instruments I used, of non-ignorable non-response overall. However, I'm going to slice it by Midwest, and in a second, I'm going to slice it by party. In this pattern, we see a negative. So that means of a negative gamma. So in the Midwest, if we focus only on Midwestern voters, the people who don't like Trump were more likely to respond. That's what a negative gamma means in this context. And then what does that mean? So here I have Trump approval, the estimated Trump approval on the y-axis, and I have the two for the whole population. The observed sample is about 40% approval, weighted sample 40%, and doing my thing, it's a little lower, but not significant. It's 40%. Now, the green lines are Midwest. In the observed sample, I think it was 44%, I forget. When we did the darker one, I'm trying to indicate that that's the weighted, the conventionally weighted. Trump approval actually goes down, waiting for traditional covariates of race, gender, and so forth. But then using this tool, gamma y was positive. That means there's signs that the people who didn't like Trump are more likely to respond. If you net that out, your estimate goes up because it's, for the whole population. And we go basically from, let's say, ballpark 45 to 50%. It's a little hard to hear to see, but as I recall, that dark green line is a 50%. Is it right or wrong? We can talk about, there's a lot of assumptions in here, but I would take this at a minimum as this is a red flag saying that in the Midwest in 2019, there's signs that there was non-ignorable non-response that was leading us to underestimate Trump support. And then, of course, in the 2020 election and in the 2016 election, polls in the Midwest tended to understated Trump support relative to the election outcome. Let me do the Trump approval, and then I'm going to do race, and then I'll turn to questions. So Trump approval, now we're going to break down by Democrats and Republicans. It's a little, anyway, so of Democrats, most Democrats don't approve of Trump, so it's like very small. So I'm going to focus on this not strong disapprove, which I know is a little bit wonky. But of Democrats, I think only 7% or so approved of Trump. But of Democrats, we're now like 30% or something, like 70% strongly disapprove of him, but 30% just weakly disapprove of him, right? In a standard kind of, there's a gradation of how strongly you disapprove. So looking at that, what this is saying, so I'm focusing on the second bar there. If we're just looking at for Democrats, whether or not they strongly disapproved of Trump, the gamma Y was statistically significant and indicating that of the people who really wanted to talk about politics, they really disapproved, they were strongly disapproving of Trump. And the people who were less eager to talk about politics were less likely to strongly disapprove of Trump. And then the bottom line, there's a similar kind of thing going on. In fact, let me just explain it with this figure. And so I'm focusing on the not strong disapprove among Democrats. Those are the blue bars. So on the raw sample, it looks like about 17–18% of the sample did, they disapproved of Trump, but just weakly. Weighting is basically the same result. But in light of this, the pattern we're seeing with regard to gamma Y, we actually see that, hey, maybe there was among Democrats, now we're at 30% or so of people not strongly disapproving of Trump. Among Republicans, we're getting kind of a similar thing. Among the strong approve, there's somewhat of a relationship overall, but now just of Republicans in general, it's about 50% strongly approved of Trump. We reweight using conventional methods, still 50%, but we reweight using these methods, or in this case, it was the doubly robust, but it's the same either way, is that actually the estimate would be, what is it, a good 10–15 points lower. I'm perfectly open to being, skeptical about that number being exactly right, but I do think this is a signal in the data that there could be non-ignorable non-response, and that there could be that in fact, among partisans, among Republicans, we're more likely to get the really intense pro-Trump Republicans in a survey than otherwise. The last thing that I will do is racial conservatism and just focus on the Democrats. We asked, a question, a variety of questions, a standard racial conservatism battery. This is just one of the questions. Let me just focus on, in the whole population, we don't really see much going on, but among Democrats, what this is saying, that 20%, this light blue line here on the Democratic line, in the overall sample, 20% of Democrats were giving a racially conservative answer. I believe this question was one about whether Black athletes should kneel during the national anthem. If we reweight the data, it's the same thing. But if we use these techniques, there's evidence that, the gamma Y was in this case negative, which means we are understating the conservatism of Democrats in that population. And in fact, the population just kind of working through the way the model works out, that in fact, perhaps Democrats more generally were more conservative. In other words, non-ignorable non-response may have led to a too liberal view of what Democrats think about that particular race question. Okay, so I know there's a lot there. There's other stuff I could talk about, but I'm really eager to hear your questions and have a conversation. The big picture, I don't think that this resolves it and finishes everything and so forth, but I just think in this, where we are, we have to take non-ignorable non-response much more seriously, given low response rates to probability surveys and given non-probability surveys. I also think that we've underestimated what we can do, and that there are these models, that work. That just, all I did is I just wrote down a model where I had a gamma YY in the response equation, and then just see what I can do with that. And Sun et al. In particular flesh that out, but of course other people as well. And that just both here, hopefully you got some flavor of, but in general, it's the randomized response instruments that really work for this. When we do it, I do see a fair bit of heterogeneity. We saw some on a regional basis. I didn't have time or show this, but other regions were in the Midwest, we are seeing and understating Trump support. In other regions, we are not seeing it. So it's not like it always finds non-ignorable non-response. And then a general pattern that I've kind of been alluding to, but is really strong across all the 5 versions of this now, is partisan. If you look at a partisan subsample, if you look only at Democrats, those Democrats we hear from are more liberal than all Democrats. The Republicans we hear from are more conservative than all Republicans. When we step back and we're looking at the whole population, the kind of the leftward bias of the Democrats and the rightward bias of Republicans kind of washes out. So it's quite common in my results, and there's a lot of other results that I haven't had a chance to show here. It's quite common to see no sign of non-ignorable non-response in the full population, and yet very strong signs of non-ignorable non-response in the subpopulations. So anyway, and then doubly robust, yeah, it's great, but it doesn't honestly, any one of these. And then I have other results using Heckman selection models and copula models. I actually have a suite of results. They all pretty much point to what we've seen here. So I don't think doubly robust is like a uniquely great answer per se, but I think it's, it has these nice features and it certainly should be part of our toolkit. Okay, so I went a little longer than I planned. I apologize. So, but eager to hear your questions.
Thanks so much, Mike. That was a great presentation. Well, we can now open it up to questions. You can put questions in the chat, or if you'd like to ask a question, you'll have to raise your hand and Ching will unmute you. While we're giving people a minute to put in the chat or raise your hand, which you can do under the reactions option. Mike, I had a question. I'm really interested in the randomized response instrument, and I'm wondering for the survey that you conducted using Ipsos's knowledge panel, how did you determine for the experiment? So it looked like there was a radio button, so respondents have picked one option, whether they want to respond to politics, sports, or something else. Just because, I mean, if someone doesn't pick politics, does that mean that they're unwilling to respond to politics, or that that's not the category that they most want to talk about? So I'd rather talk about sports, but I'm happy to talk about politics too. And does that difference really matter?
Right. It's a great question. And there's I've thought about it a lot, and I have other, analyses of this. So one thing that I didn't get a chance to say, what I actually do is I say this question, and then the people who pick, say, sports, I ask them 2 questions about sports, and then I come back and ask them all the politics questions anyway. Right. So it's a little ambiguously phrased here. So I never promise them that I won't come back to politics. So I am able to, for example, to see that of the people who talk about sports, I haven't done a super thorough job of this, but there doesn't seem to be any differences in whether you pick movies, health, or sports. But of the non-politics people, they go in the direction, by the way, in this, everything I showed you here is I just throw them out, right? But by the way, I have seen what they think about politics, and all those patterns are, like, for example, in the turnout of the people who choose, so it's only a subset of people who get the choice. Half of the people get a choice. Of the people who choose politics, they're all saying they're going to turn out to vote. And of the people who choose movies, sports, or health, they are visibly, and I even could pull it up, I could show you the numbers, they're visibly less likely to say they're going to turn out. And the other patterns about Trump and so forth persist, especially the party-based stuff.
Okay, thanks. Yeah, that's helpful. It's really interesting. Elizabeth, I see you have a question. Ching, can you unmute Elizabeth?
I think.
Yes.
You're good. Yeah.
Yep.
Okay. So my question is related to this being about estimating means using survey data. I'm thinking about the parallels with estimating the average treatment effect when you have a treatment group and then you choose like a matching group or a non-equivalent control group. And so could you just talk about the parallels between these 2 sources of kind of the initial selection and then within that selection, in this case, it would be the assignment of the treatment.
Yeah, let me try, but then please come back if I'm getting it right. But I think I get it, here's what initial take on this is, so I'm just estimating means, but now you could be estimating, you have a treatment, you show someone a message, you're A/B testing, you show someone a message that says Biden's too old or whatever, and then you see the effect of that. In general, this is going to be then situated where you can get, I mean, first of all, there's just a crude version, or it's not even crude, but a less model dependent version we could kind of do in the spirit of what Katherine said. I can just look at the people who chose to talk about politics, see what the treatment effect is there. I can look at the people who didn't choose politics, see what the treatment effect is there, right? We can just see. And by the way, my intuition is usually it's probably not going to matter, honestly, but especially in politics stuff, I just think the way a sophisticated person who loves talking about politics is going to respond to some political message may well be different. So even though in general it may not matter, I'm quite open to, and I think it's quite relevant in today's environment, that the less interested and engaged folks, the treatment effect may be different. And so you can estimate this. You can go through and kind of do like those are means, but if you had a beta hat or a beta on some, RCT type thing, it's going to follow. Basically, it's going to follow through, and you're going to be able to assess those things. And actually, just even as I'm saying this, I'd actually have to think about exactly how to do that, other than, again, I gave like just the not model dependent version of the people who want to talk and not want to talk about it. But you can roll, it's like a lot of things, like the properties of a mean carry over to the properties of a relationship such as beta. And then you've seen, I'm sure, there's a lot of other work where, like the kind of effects you see on mechanical Turk in a RCT are the same as you see in a serious, probability-based poll. And that happens a lot. And so maybe that's what we would see here. But I just am a little nervous about that. And so would like to have, and this, I think, would get you a couple slices, not only the doubly robust element of it, but just even the thing I was talking about here. You get a couple slices as to see if the effects seem heterogeneous or not.
Thank you. See a question from Phil.
Again,
Oh, I think you just got muted again.
we both unmuted each other.
Okay.
So I think, I was going to ask this question because I've been asking you this question on the internet for a long time. So I know how to do the IPW because in survey statistics, we call that a calibration equation. I know how to solve a calibration equation. What I don't know how to solve is the imputation equation. So how do you solve it? You just have software that solves it for you?
Yeah, I mean, so yes is the short version of that, but let me just show and then see if maybe I can get, and I'd be happy to give you the code. And by the way, a code is just what I got from Sun et al. So I don't want to pretend that it's my original code.
That's
but
nice. It's probably R though, right? Not SAS. But I know people who can tell me R, explain R to me. So that's
yeah,
okay.
it's all definitely R. And it's not, it's really not that, I don't want to say it's this thing, sorry, that bottom of this slide is kind of ugly.
Yeah, that's the hard
thing that you maybe there's just, I can give you the code that they developed that, but it embodies this. And it's not that bad really. It's actually the standard errors on that thing. That thing is, there's just a lot of like kind of brute force kind of stuff with the, the Hessian and all that. That's a little ugly, but this is, I don't know, anyway, you can, anyway, I'd be happy to share with you the elements of it, but the sequence is not the sequence. Let's see, do I have the sequence here? The sequence is, really not that, and the sequence is fairly commonsensical. As you're estimating, first you just estimate f of y given r, of the people you have.
Right.
Weird thing is you're throwing z into there, and I just have been spending all this time telling you z doesn't matter, but again, r equals one population, z matters. You throw that in. They do a saturated model. They do all the interactions, and once you get that thing, the other steps are just kind of brute force.
Does it hop down to the last one right away and just try to solve it that way?
Pardon me?
So the last formula, which is the other page, the one with the z minus z hat, was the z minus z hat. Z minus z hat one. The second to last.
That.
Do you just sort of figure out what that guy at the end has to be for that thing to be equal to 0?
Yeah. Okay. Very good point. So basically, you've done all this stuff, all those things. Then you see the y hat 0, and you're right. It is not at all obvious in looking at this, but in the y hat 0, there's a gamma y floating around. And so now once we've done all that other work, there's that last step is there's only one parameter to estimate, which is the gamma y.
Okay. Yeah.
But as an aside, it turns out, and that's why I'm a little bit not like really selling the doubly robust too hard, is whether we do the imputation model that's maybe a little more, to me, a little more commonsensical, if that's a thing, we end up with gamma y's that are really quite similar across the two models.
Yeah. Well, that might be, I said it's intuitive, but it's not as intuitive to me how you get expected value of y0 given r0. I know it has something to do with basis theorem. Whereas the other part, which you think is the hard part, the IPW part, is to me just a calibration equation. I have software that establishes calibration equations. So
Yeah, I mean, for what it's worth, I find this more
I'm perfectly
intuitive.
happy to
I
do
think
it.
we're on the same
I'm
page.
perfectly happy to do that. That I can do, but the other part I
Yeah.
can't do, and that's what confuses me. But I got up to this part, and I can't be W or bust until I do both of them. And oh well. So you just have to send me the code.
I'm seriously, send me an email.
Translate it to me in English.
More than happy. It's not complicated code. And then the other thing is, honestly, just my sense, like I've done this with Heckman, I've done it with Copulas, I've done it with the imputation, I've done it with the IPW, you know, I'm getting kind of all the same thing. So I honestly,
I'm old. I can't learn new stuff. I just plan to do the stuff I know how to do.
Yeah, I think to me, I think the W robust is kind of marginally, it's interesting, but if you do this and get results, I think that's worth a lot.
Okay, sorry for taking so much people.
No, you're good. Thanks for the question, Phil. Vladislav asked a question in the chat about the slides. Would you be willing to share your slides, Mike?
Yeah, absolutely.
Thank you. So I think you can either email Mike or you can email me, and I'm happy to pass along any slides. Travis, I see you have a question.
I do. Thank you. And Dr. Bailey, thank you for a good presentation. Just a point of clarification before I get to my question. It seems like when we're talking about non-response here, we're talking about instrument non-response. Is that right? Kind of overall, whether they agree to take the survey or
not? Yes, I have done, and like this project is kind of taxed my capacity a little bit. I did in an earlier version. I would also have a question where I would say, do you want to, I would do this, I basically kind of what I would call unit non-response, you know, as you point out. I also did do an item version of where I said, would you like to answer race questions? Or I forget exactly what I said. Again, I just haven't had time to go. When I initially did that, I wasn't really seeing a lot is the short version, but also, by the way, a lot of water has passed under the bridge. I feel like I've got kind of a better sense of these methods and so forth, and I would like to revisit that. But I do think you could, or I do think you could imagine an item version of this as well.
Yeah, that was going to be my question, is whether you think the logic of instrument non-response and its relationship to the outcome of interest, if that logic then extends to item non-response. So if I'm willing to answer the survey instrument, but I'm not willing to give my thoughts about Trump,
right?
Does that same logic extend?
So yeah, and then one of the things, and this is like of the people who kind of push back on this, and of course there are people who push back on anything, including this.
No, not in academia.
Is like, this is a local effect, right? So that, you know, the politics, sports, healthy movies questions, a very kind of specific way to be pushing people in or out of a survey sample. And you can imagine other ways to push them in or out. And that's, let's say we do it on an item and the item is, you know, related to race or something. And that would be kind of a different set of people are getting pushed in and out by that, right? So I'm quite open to maybe on certain things you have to do that. But I will also say, or I should really emphasize, that even with this approach, which is more unit non-response based, the analysis proceeds question by question. And again, many questions, especially when we look at the whole population, I see no non-ignorable non-response, right? So even with the, you know, so it's even with the unit non-response setup that I've been describing here, the results vary by question. And again, like turnout, all 5 times, I always see the pattern I just showed you. Trump, I maybe once, you know, I did Trump at different times back to 2016, by the way. And I think maybe I saw overall some pattern, but usually it's kind of comes and goes. But the Democrats being more liberal, the Democrats who respond, you know, the non-ignorable non-response going in opposite directions across the parties, I see always, but again, it's question dependent.
Phil.
Well, I hate to contradict you, but I will. You could look at your H1, H2, and H3. It's the same pi I, no matter what the question is. But H4 is question specific. It has to do with a particular YI. So it's really more for item non-response than for unit non-response.
No, so fair enough. I think that's a clarification I'd accept. I would just say the way I set it up is once you non-responded, I was throwing you away for the whole survey. In that sense, it's a unit non-response, but I absolutely agree that it depends. A different Y, a different question, you're going to get a different. Of course, very, very clearly, I get a different gamma Y for each question. Absolutely, and often there's 0.
All right. Vladislav has a question. I think you should be able to unmute.
Yeah, and unmute. Saying yes, thank you, Katherine, and thank you, Mike, for nice presentation. On this particular slide, I wanted to ask, what is this estimate of of ZI? Because we only talk about estimate of pi I, but here we have estimate of ZI. What is it?
Yeah, good. That's a helpful clarification. So in the in Sun et al., the way they set it up, ZI need not be randomized. So ZI could depend on X. And so ZI hat, you actually have to kind of like the ZI hat here, so thank you, I did not clarify this, but ZI hat, they actually have a stage in their code. I'd be happy to share their code. You can get it from them also. The ZI hat is ZI conditional on X. But for all, since ZI in the work that I'm presenting here is randomized, then ZI hat is basically just it's just Z bar or something with normal sampling variation. So loosely, if you want to just approximate this or try to get closer to the intuition, is just imagine, like in this, I have ZI as the proportion of people who have the treatment is 50%. So loosely speaking, when you see ZI hat, put it with 0.5 in there, and to help get the intuition, that would be more or less accurate.
Okay, thank you.
All right. Thank you very much. I think we'll wrap it up here since we're a little bit over. Mike, thank you so much for giving this presentation. It was really interesting. And thank you all for attending. This presentation was recorded and we'll be posting it on the WSS YouTube channel, so you can keep an eye out for that. And if you're interested in the slides, you can either contact Mike or myself. I will put my email address in the chat. If you have any suggestions for topics or presentations that you'd like to see, please feel free to email me. And upcoming seminars will be advertised via email and also on the WSS website, and I'll put the link for that in the chat as well. Thank you all for attending.
All right. Thank you, everyone. Very helpful.
Thank you.
Thank you, Katherine.
Yeah, thanks, Mike.